And I'm Pat Watson, and I'm going to introduce our next speaker, who is Mark Allen. So let me just do a quick bio. So Professor Mark Allen, he is the Alfred Fittler Moore Professor of Electrical and Systems Engineering here at University of Pennsylvania. He is our site director at MANT, which is the Mid-Atlantic Nanotechnology Hub, and it's one of the NNCI nodes. And we're headquartered here at the Singh Center at Penn. And he received his PhD from MIT, and he co-founded several startups, including a very interesting one, CardioMEMS, which developed a wireless implantable MEMS center to look at cardiovascular systems in people. And I will now turn it over to him. Okay, Mark.
Thank you. Thank you, Pat. I'm eager to tell the group some of the nano IoT research that's going on here at the Mid-Atlantic Nanotechnology Hub. Before I jump into that, I wanted to give you just a very brief overview of our center. So we are located here in Philadelphia, where the star is. And you can see that we're in the fortunate situation of having a relatively large number of colleges and universities within driving distance of our facility. And so when I tell you a little bit about the users and the kind of people who come, you'll see that we have a nice representation of both university and industry users. We like to think of ourselves as a catalytic force for nanotechnology. Not only does that sound good, but more importantly, it means that we contribute to the success of others, right? We try to catalyze the success of others, which I think is a common feature of all of the NNCI nodes. We try to help people take fundamental advances in nanoscience and turn them into technologies by basically having a makerspace for people to do nanofabrication and nanocharacterization. Our facility actually comprises 4 under one roof. The Quattrone nanofabrication facility, where we do fabrication, 2 characterization facilities, and we also, through MANT, have a partnership with the Community College of Philadelphia, where we are working on developing and providing nano-infused educational programs for associates level students. In terms of our user base and what they do, starting in the middle, we have about 60% internal users, about 40% external users. Of those external users, looking on the right, about half are from these colleges and universities that are close by. The other half roughly from large and small companies. And then if I look at what our users do, and I think this is important as we start to think about nano IoT, looking at the capacity utilization on the left, we find, like many of our sites, that a third of our users are in the material space, but we have very significant representation from life sciences and medicine, quantum physics and optics, and MEMS and mechanical engineering. And we think this synthesis of MEMS and related electronics is a key part of what we're trying to define as this nano-related, or nano-enabled, excuse me, Internet of Things. So with that as a just brief overview of our site, if you want to see the tools and all of this, we have a very easy website to remember, nano.upenn.edu. You can take a look and see some of the tools that we have. But I want to spend most of my time talking about some of the interesting work that the users are doing associated with this nano-enabled Internet of Things. So as I said in the very beginning of this symposium, when I was introducing the concept, it's, I think, our conjecture that many of the things in the Internet of Things will be nano-enabled. And of course, when we think about those things, they could be transducers, at their heart, right? Sensors, actuators that are going to be interacting in some way with the environment, and then turning that interaction, that physical measurement, into some sort of electronic information. But as we heard from our invited speakers today, and I was really enthused by some of the things that we saw, that may be necessary, but it's by far not sufficient. That we need to think about power sources, energy harvesters, low power circuitry, um, and also how we can get that information, probably wirelessly, from our things back to some sort of central repository so that that data can be processed and actionable information and actionable steps can be taken. And that might mean RF, probably does mean RF in a number of, in many applications, but it could also be optical communication, optical interrogation. It could also be what I think of as physical data transfer, so ultrasound, things like that, that might allow us to get data from one point to another. So we have users with research focused in these areas, and I'm going to go through and spend the bulk of my time just showing you some examples. And hopefully from that, we can glean a little bit about what kinds of fabrication technologies these users are using and where this field might be going. But before doing that, I wanted to sort of give you my chunked thoughts about where these application spaces are that our users are looking at. Obviously, we've heard a lot about precision agriculture, and I'll show you one more example of that in my presentation. Medical and biomedical applications. The Internet of Things could also be thought of as, say, the network of patients that a particular physician or hospital has, and getting that information into the hands of medical providers. Could also imagine that a body network could be an Internet of Things, where if the body is studied with wearable and or implantable devices, that information could be co-located into one point for subsequent medical treatment. And then finally, energy, which I think is going to be a key enabler. Even if we manage to minimize the amount of energy that is consumed by these nano IoT devices, we still need energy sources in some way. So these are the application spaces that we see here at MANTH. So let me go through and show you some examples. I think I have 8 or 9 examples of some of the projects that users are doing, and you can see the breadth of research activity in this area. So let me start off by jumping into a little more detail into one of the projects that Professor Kagan, who we heard from earlier today, is working on in her own lab. So an interesting question about some of these sensing devices for precision agriculture is, could we manage making them so inexpensive that we could crop dust them, say, from an airplane? We could fly over a field, we could deposit them everywhere, interrogate them, and then have them biodegradably dissolve away. So here's one example of how you might be able to do something like that for moisture sensing. So suppose, for example, that I have a hydrogel material, and on this hydrogel, I put arrays of photonic emitters. So here's an example of such a structure. The scale bar is about 500 nanometers or so. And the physical extent of this can be on the order of millimeter to centimeter scale. The reflective signature of this periodic structure is going to depend on the physical spacing between these nano antennas. And that physical spacing is going to depend on the degree to which hydrogels swell. And the swelling of hydrogels is going to depend on the local moisture content. And so we have the possibility of distributing devices like these and having them be different colors depending on the local moisture content, and then reading that out with, say, a flying drone or some other optical interrogation means, all without having to have any electrical contact to these devices and having them dissolve away after they are no longer needed. A second application that one of our users is doing is looking at sensors for COVID-19. So of course, there are many such devices available now, but this one I think is particularly interesting. And so let me explain how this works. The key feature of this is that it's a chip that can be read out with a smartphone optically. So not chemically, but optically. And the basic idea is that if I have a chip, and here it is here, and I place on this chip a mixture of the following things. Some sample, biological sample that maybe came from someone's nose or saliva, and some nanoparticles that have the one end of an antibody attached to them. And the other end is protein that I'm looking for. If I have these, all three of these components together, you could think of this as one end of a socket, this is the other end of the socket. If there is COVID-19 proteins available, then these will all bind together. And if this guy is a magnetic nanoparticle, and this one is a catalytic one, I can drag these particles down into a microwell array, and then I can add some hydrogen peroxide to this array. And what I'll find is that those array elements where nanoparticles were dragged down into the bottom of the array catalyze the release of oxygen. So if I have the protein that I'm looking for of interest bonding a nanoparticle and a magnetic bead, I get a bubble. And if I don't get a bubble. I can then take this, use a cell phone camera, look at my chip, and then use machine learning algorithms to determine whether or not I have a positive or negative reading. So I really love this project because it is a synthesis of, I think, all the Internet of things that we've talked about, right? So we have a microfluidic chip that's nano-enabled. We have a smartphone, which serves as both as the readout as well as the communication means to send that information to a central repository. And we have an app based on machine learning that allows us to accurately detect whether or not this particular patient has COVID-19. So very interesting application, I think, of nano-enabled IoT. Here's an example of looking at sensors that are on the tip of microneedles. So if we look up here, we can see a number of these microneedle devices that have been singulated. And if I zoom in on the tip of, if I zoom in on the tip of one of these microneedles, then what I'll see is an array of microwells that look something like this. If I functionalize that array of microwells with, say, some antibody that's looking for a particular protein, and I monitor the impedance between two electrodes in these microwells, I can detect binding events of protein when they bind to these antibodies. And the nice thing about using microwells in this particular case is that it allows me to get a lot of surface where I have electric field lines concentrated, where I can do impedance-based interrogation. These sorts of devices have been shown to detect cytokines with very good correlation to the gold standard of ELISA. But the interesting thing about them is that unlike ELISA, where you would take a blood sample from a mouse, say, and then send it off to a lab and you would get reading back, here you can take one of these devices, stick it into the mouse, get a reading right away in real time, and then potentially be able to act with some sort of medical intervention in real time. Again, something enabled by the nano possibilities of creating these microwells. Here is an example of what I was talking about before with a body Internet of Things network potentially. So this is a project that's being done at the medical school, Penn, in collaboration with electrical engineering, to look at the possibility of building mechanoreceptors. So if you have patients who are have lost sensation in their hands, this happens often, I'm told, with say diabetic patients. Could you imagine implanting a mechanoreceptor in the fingertip and having that mechanoreceptor tell me something about normal and shear forces at the fingertip, powered by and communicating to a wristband, say a watch worn on that hand, which then goes and communicates to a stimulator, which could stimulate peripheral nerves to give you back a feeling of sensation. So that's the conceptual idea, fusion of MEMS technology to build not only a biocompatible package, but also a capacitive pressure sensor, ultra low power electronics, as well as pickup coils for energy to create these structures. And here you can see one of these devices on fingertip. Ultimately, the idea is to implant these and have them be completely unobtrusive from the perspective of the patient and yet restore sensation. So it's not just sensors, but also we can think about actuators. So Chris Ober showed this beautiful work that was done at Cornell University, and mentioned that the professor who did this at Cornell, was graduate or postdoc at Cornell, has come to Penn as a professor, is continuing this work. But the idea behind making these small actuators, here you can see a scale bar of about 20 microns or so, that can move and swim, is really quite intriguing. And I think the technology here is very interesting. So as actuators scale, it becomes more and more difficult to be able to maintain forces, right? So we all know that from scaling laws and arguments. Is it possible to make small scale robots that can actually move? So one of the ways to do this is to try to draw that capability of motion from the environment in which it is embedded. So these devices utilize a very interesting technology where they harness gradients in ionic strength in fluids to curl and uncurl actuator, very, very thin actuator structures. And the way these gradients are induced is by means of a small photovoltaic device that's integrated on these structures. So you can have these devices powered by light, following around light, doing lots of interesting things. And you can see that the speeds of these devices are actually not very fast, but the fact that they can move and move deterministically is really quite fascinating. Parenthetically, those of us who were kind of in the early days of MEMS remember the, robots will run around and clean out your arteries. And of course, that didn't happen. And we went through the hype cycle to the crash at the bottom. But maybe now, after 30 or 40 years of MEMS research, we might be finally ready to start to think about such things. I mentioned energy as an area. So there are researchers at MANT who are looking at creating micro and nanostructures to allow us to get larger amounts of energy per unit volume, increasing the volumetric energy density of batteries, which of course is going to be very, very important for miniaturizing nano IoT structures. So within material science, we have people who are building nano heterojunctions who are looking at materials that are maybe not so exotic so that things can be made very cheaply. Another key characteristic of nano-enabled IoT. And also looking at materials that are able to be engineered to have multiple length scales. So for example, I can simultaneously have very high surface area for battery electrodes and yet some channels to allow bulk ionic flow so that I can get reasonable power densities, say to charge or discharge these structures rapidly. Professor Kagan also mentioned the possibility of biodegradable batteries. So here's an example of some batteries that are being made out of zinc, a biodegradable, fairly energetic metal, carbon-infused paper as an air cathode to build a zinc air battery with a hydrogel in between as an electrolyte. So you can imagine that these relatively innocuous materials can dissolve away when we're finished with them, yet at the same time, we have the possibility of being able to generate pretty significant amounts of energy. So this is an example of one of these cells discharging to almost 800 milliamp hours per gram of zinc, which is close to the theoretical maximum for zinc. And so right now we're looking at things like, is it possible to bury air batteries in soil? That sounds kind of strange, right? But it turns out there is enough air down there for these air batteries to still operate. And we're looking at the biodegradability and also the influence of these power sources on the plants that they are embedded near. We heard again about how important power is and power management. And so we have a number of projects ongoing at MANTH where researchers are looking at both algorithms as well as hardware to be able to take the same power source that in some cases, say for an RF transceiver might last for a month and have it last for much, much longer. While still being able to transmit the same amount of data. And there are a number of ways in which this is being pursued. And then some of this is happening at MANTH and some at other sites and other universities. We could have all passive devices. We could have devices that don't require any power until they are woken up. They don't have to stand by and wait. They only have, take zero power to wake them up. We heard about pushing the technology of low power circuits to get nanowatt scale machine learning processors. That sounds crazy, right? But it turns out that that is now possible with advanced CMOS. And then sensing and processing in non-electrical energy domains. If you're looking at, say, an infrared sensor, maybe you can do some information processing in the infrared before you put it in the electrical domain and start to add up, chew up battery power. Just a couple of other very quick things. There are users, industry users who are building light emitters. So we can imagine optical, active optical communication, not just passive optical communication. And there are researchers who are looking at the possibility of encoding information, not just in, say, time division multiplexing or wavelength division multiplexing, but looking at the interaction of ring resonators to make lasers that have different orbital angular momentum in the photons that are emitted. So yet another way that we can encode more information so that with the same pulses of light, if you will, we can encode more information and therefore have more efficient use of that highly valuable power. And then my last slide, I just want to mention a couple of startup activities that are going on. One in the magnetic space where researchers have developed a way to build up multi-layers of magnetic material and insulation material in sequential electrodeposition to allow them to build thick cores that will allow us to be able to shrink the size of power conversion components and create compact power sources for nano IoT. And in the biomedical space, researchers developed devices that would allow microfluidic-based sampling of blood for various disease states, put this into a reader, have the reader be connected to a smartphone, and then that information being sent over the internet to physicians. So I know this was a lot of information from a lot of people, but I think that, let me stop my sharing here. But I hope it's given you a little glimpse of some of the things that are going on at MANTH in the nano IoT space. And if you forget everything that I said, which you may, just remember one thing, which is we have this tremendous user base here who's very interested in pushing forward this research area. So with that, I should stop and take any questions.
Thanks very much, Mark. Do we have any questions?
Well, we have a comment from Kevin, but I think, yes, we all, those of us of a certain age all remember that.
So maybe I'm gonna make a sort of question. So we have the symposium to try to bring together people from all these disparate, I guess, technical fields, to people from communications, computing, sensing. How do we do this on a larger scale? Like, is there a nano IoT conference that could bring people together at a national scale or international scale?
I think that's an intriguing idea, and certainly one that we should discuss, certainly among the site directors after this symposium is over, and then maybe even at the meeting. I think it would be wonderful if a meeting like that existed and we're driven kind of literally from the bottom up, because we're kind of at the bottom of this nano IoT activity. It might also be possible to look at some of the existing IoT meetings and seeing if there is a session or a possibility of organizing something where we have a nano focus, where we could come together and perhaps interact with that community. But that's a great idea.
Do we have any questions? All right, well, thank the speaker, and thanks, Mark. And we'll move on to our next speaker.